Okay, so we were saying that it depends also on the geometry. So we should always start from the equations and do the simplification. And if we have this application with variable area, not constant area, we can say that the heat rate is constant, but not the heat flux. Why the heat rate is constant? Because if I consider any control volume, I can say that the rate of coming in is equal to the rate getting out. Okay? But if the area is changing, the flux will change because the rate is written as minus K times A1 times dt by dx at x1. It's equal to minus K times A2 times dt by dx at location 2. Okay, so if I have variable area, I say the rate is constant in pure conduction steady state problem, while the rate is variable. However, if I have constant area, which is the case in my problem of the wall, then I can drop the area and then say also the heat flux q second will be constant. So you have the right from now on, if you have a steady state application where you just have pure conduction and the area is not varying, you have the right directly to say that your flux is constant. And because it's constant, then you have linear variation of the temperature with x because the gradient is constant. So you can say directly that the heat flux can be written as K del T over L, where del T is the absolute variation of temperature, T1 minus T2, over the thickness L. Any question on this? So here we can resume what we said. So we have the heat rate is minus Ka dt by dx, and the heat flux is minus K dt over dx. Now, in general, as we mentioned before, some materials conduct heat better than others. Materials that transfer heat well are called conductors. They are characterized by a high thermal conductivity. In general, metals are good conductors, while wood, paper, and plastic are not. Materials that stop the transfer of heat are called insulators, like wool and fiberglass. So whenever we select the envelope of the building, we should select materials with relatively low conductivity to ensure high insulation properties of the envelope and reduce the temperature variation within the indoor space. And of course, if we have good insulation, we can reduce the heating and the ventilation demands, so we can also reduce the energy consumption. In this table, we can see conductivity of typical metals and fluids like water and air. And as we mentioned before, air is characterized by a relatively small conductivity, which make it a good insulator. This is why we introduce an air layer sometimes in the envelope of building. Let us do some examples to practice with heat transfer. So here we have the wall of an industrial furnace is constructed from 0.15 meter thick fire clay brick having a thermal conductivity of 1.7 watt per meter Kelvin. Measurements made during steady state operation reveal temperatures of 1400 and 1150 Kelvin at the inner and outer surfaces respectively. Yeah, just 1 second. Okay. What is the rate of heat loss through this wall that has an area of 0.5 meters times 1.2 meter on a side? This problem is very simple, but I will give you actually what we do. And I will give it in another way. in general, this is what we know. We know the conditions at the inner and outer environment. We don't know in general what is the temperature of the surface T in and what is the temperature of the surface T out. Okay? In general, we don't know these temperatures. We find them by calculation. Okay? So in general, we know, for example, this. They can tell you, I have the sun. We know the irradiation from the sun. For example, they tell you we have an irradiation of a G equal, for example, to 400 watt per meter square that is hitting the surface. We have wind blowing over the surface, let's say, with a convective coefficient that will be given. So we have H of wind and temperature of wind given. Okay, so let us put here T out and here Tn. Okay, now from the inner side, we can tell you, for example, that we have natural convection. So we have just air. Okay, and we give you T of air and the convective coefficient of air from the inner side. And now you want to design, for example, you want to decide on the required insulation to reach a certain desired temperature. So this is what things happen in general. We impose what is the temperature of air we want to reach. We know the outdoor conditions. We try to know what should be the insulation properties of the envelope. So sometimes we don't put only, of course, one layer. We can put several layers, and we'll discuss this also in next chapter. So we'll see how we can put several layers and how in this case we account for conduction, so total conduction in different materials, and how we consider the total resistance provided by these layers. Okay, so this can be complicated much more than what is given here, but always the approach is the same. What I should do, I should perform an energy balance. Okay, and then the application of this energy balance will allow me to relate the heat fluxes. Here, for example, since it's a steady application, what can I say? I can say first, if I take the first interface that I should consider is with the outer environment. Okay, so as we'll see at the end of this chapter, one good strategy is to take a very thin control volume at the surface. Okay, because when I do this, whenever you take this thin control volume, you can see what is happening at the surface level. And plus, in case you have storage, in this example we don't have storage, but in case you have storage, whenever you take a very thin layer, okay, the volume that you selected is negligible and the mass is negligible. So whenever you take a thin layer and you perform the energy balance, you have no storage for this. Okay, so always, even if you have an application including storage, when you take the surface, you take a thin layer at the surface, you have no storage for this small control volume, and then you can write through this surface layer, I have sum of energy in equals to sum of energy out. And if we take, for example, this case that I gave you, okay, what is coming in this thin layer is the irradiation of the sun, and not all of it, of course, because as we'll see now in a while, when we define the characteristic of radiation, we'll see that a flux that will reach a surface by irradiation from any other surface will have a proportion that will be reflected. So one part will be reflected out. It will not enter the surface. So we have rho g that is not entering, and we have a part that will be absorbed Okay, so in K, and we have a part that will be transmitted. We'll discuss all of these in a while. So here, let's say if you have an opaque surface, you don't have a transmitted part, you just have an absorbed one. So let's say you have En is alpha G. This is the absorbed energy from a radiation effect. Okay, and you have, of course, the convection, because you have a fluid moving over your surface and it has a hotter temperature than your surface. So heat will be transferred by convection from the air, from the wind towards the surface. So you should add plus uh, convection at outer side. So Q convection out. And also in a while, we'll remember together how to calculate this rate. So this is the fluxes coming in. And what is getting out of this surface layer? Can you tell me which type of flux will go out? Which type of flux will go out of this thin layer?
Heat by conduction.
Yes, very good. Heat by conduction, okay? Because I am then within the solid material, and heat within the solid material will be transferred by conduction. So this equation will allow me to calculate the conduction flux, uh, and or at least to relate, if you want, T out, okay, to the temperature at the surface. So I will not be able to calculate the value of this flux now, but I will be able to relate T out with T surface. And I will say then, once I am within the solid, the conduction flux is constant. So I can find the expression of my conduction flux, and it will be equal also to the flux convected to the inner space. When I use that alpha G plus Q convection out is equal to Q conduction, is equal to a Q convection to the inner space, I will be able to solve for my variables. Okay. We will discuss this in detail in other examples, but here I just wanted for you to know the overall picture of the problem. Here, because just we discussed conduction, we didn't yet discuss radiation and convection, we have a very simple application. They directly gave us the temperature at the surface without knowing what is the source of heat. Okay, so we don't care here how heat will be transferred, and how it will get from outside. Why? Because they already gave us T surface 1. Okay? If we don't know it, we need to know all processes taking place to solve for T surface 1 and T surface 2. But here they are given. So all we have to do here, since we know T surface 1 and T surface 2, and we know the conductivity of the material, and we know the area of the wall, we just have to say that the heat rate of conduction, and because they asked for a rate, so I should multiply by the area. It's K times A times delta T over thickness. Here I'm getting the absolute value of delta T because I know the direction of energy transfer here. It's from the highest temperature to the lowest temperature. So I'm just finding the magnitude of this conduction rate. As we said, just pay attention for unit, please. You know that K should be in watt per meter Kelvin. So in case you have different units, do conversion. So watt per meter Kelvin, which is 1.7. For the area, I just have to multiply 0.5 by 1.2. For delta T, it's the highest temperature minus the lowest one. And for L, I need the thickness of the wall, which is given. It's 0.15 meter thick. So here it's just a direct application to calculate the heat flux by conduction, heat rate by conduction. Now, the second important process of heat transfer is convection. And as we said, convection is the heat transfer between a moving fluid and a surface that are at different temperature. Now we'll have several types of convection. we can divide it mainly into energy transfer due to random molecular motion, diffusion, or energy transferred by the bulk or macroscopic motion of the fluid. What is the difference? Let us discuss this through two examples. The first example is similar to the ones that we already tackled about heating water or a fluid by fire. Okay, as we said, because of we create a variation in density within the fluid, this will lead to always circulation from the cool side to the hot side, because a higher density will be at the top level, so the water will tend to move downward to replace hot particles, and this will be done back and forth, because cooler particle will be heated when they go down and then they move up, etc. So this is a random motion of the fluid which is created by density variation. On the other hand, if we have a forced motion, yani we are creating a motion, we are imposing, let's say, the motion of a fluid over a surface at a certain velocity, then we have what we called convection by bulk motion of a fluid. So as the fluid will move over the surface, in case, for example, the temperature of the surface is larger than the temperature of the fluid, what will happen is that heat will be transferred from the surface towards the fluid by convective effect, since heat will be transported by this fluid. Now we'll discuss in more detail different types of convection. The convection heat transfer mode involves the combined effect of conduction and fluid motion. Why they are saying that it's involving conduction? Because in the first stage, heat mode was conduction, and at the interface between the solid and the fluid, it will become by convection. To understand more this, if you go back to the example of a surface and you blow water or air over the surface, you know that from fluid mechanics, whenever you have a surface in contact with a fluid, due to viscous conditions, the molecules that are at the proximity of the surface will have the same velocity of the surface. So let's say you have a fixed surface, you have a very thin layer of fluid molecules that is at rest. So the velocity of these molecules is zero. And convection is not possible with a zero velocity. So just within this thin layer, which is characterized by a velocity of zero, heat is transferred by conduction. So at this level, from the surface to this layer, you will have heat by conduction. Okay, but now as you go away from the surface, you start to have velocity variation. So the velocity will increase from zero to u infinity, which is the velocity of the fluid outside of the boundary layer. What is the boundary layer? Because you imposed a velocity of zero at the surface and you have u infinity, your fluid was coming at u infinity, you are creating a gradient in velocity. And because of viscous effects, the fluid will resist this change in velocity. The velocity will go from zero to u infinity. So until reaching u infinity, you have what we call the development of a boundary layer. And if you do smoke visualization, you can see that you will observe this. So you can see that the velocity will increase from zero until reaching u infinity at a certain level. And if we locate the points where we reach u infinity, we can detect the presence of the fluid boundary layer. Okay, so here what will happen once we get away from the surface, heat will move through the fluid now by convection, because the moving particles will transport this heat, and then we can say by energy balance that Q conduction will be equal to Q convection. And this convection, to be calculated, need to know the heat, this coefficient, which is called the convective heat coefficient. And this is a very complicated coefficient because it's affected by a lot of factors. It is affected by the velocity of the fluid, It's affected by the type of the surface, if it's a rough surface, a smooth surface. It's affected by the thermophysical properties of the fluid. What is the conductivity? What is the specific heat? What is the viscosity, etc. So it's really complex. This is why, in general, H is determined by experiments. And from experiments, we can come up with empirical relations. And you will see in this course, we use a lot of empirical relations. But of course, you don't have to memorize anything. I will give you any empirical relations that you need. I can tell you, by conducting experiments, we found out that the convective coefficient, its function of the velocity, of the conductivity, etc. I give you the formula, and just you have to know how to apply. So once I know H, I can say that the heat transfer by convection can be written as the heat rate is Q equal to H times A times delta T, where delta T is the difference between the surface and the moving fluid. So here we can consider a simple example. You have a surface and fluid is blown over the surface. If the temperature of the surface is larger than T infinity, the flow will be from the surface towards the fluid. Pay attention, this formula also will work if T surface is smaller than T infinity. But actually what will happen, you will get a negative result. And this means that this arrow should be reversed in direction. So heat flux will come in instead of getting out. Any question on this? Okay. So as we mentioned, the convective heat transfer coefficient is a complicated function of several parameters, including the nature of the fluid motion, the fluid velocity, fluid properties, and surface geometry. And it will be provided from experimentation. Now, what is interesting for us is to see the different values of H with gases, liquids, and also it will be affected by the type of convection. First, convection using gases is much less efficient than with liquids. Why? Because the convective coefficient of liquids is largely higher than in case of gases. And we have a lot of applications that we use liquids for convection instead of gases because of their high efficiency in convective heat transfer. We can take the simple example of our cars. If we consider the thermal engine of our car, it should be continuously cooled, okay? Because we have a combustion within the engine, and this will lead to a high increase in pressure and temperature, and we need to release heat in order to avoid if you want failure of the material, because any material has a certain capacity to sustain pressure and temperature. So if you don't cool continuously, you can have failure of your engine. Now, in the engines of our cars, we rely on two types of convection. Convection by air, because when your car will move, okay, air will be blown over your engine, so it will help into the cooling. But we cannot rely just on cooling by air, because it's not very fast. It's not efficient as the cooling by water or the cooling by a refrigerant characterized by high convective coefficient. So this is why we have circulation of water within the engine that will allow to cooling by convection from a liquid. Now, if we compare free to forced convection, as expected, forced convection will be characterized by much higher values of H. What is the difference between free and forced? Free convection relies only on temperature gradient. So as we discussed, when we create temperature gradient, we create a temperature density gradient, and this will lead to circulation of the fluid. But this circulation is not very fast. You don't have high velocities, so the convection coefficient is relatively small. However, when you blow air over a surface, you impose a certain high velocity, you can have a higher rate of convective transfer. And the most efficient type of convection is the convection with phase change. As we discussed in this course, latent heat is really very important and has a lot of application, not only in conduction but also in convection, because Convection can be associated also with phase change in case of boiling and condensation phenomena. So whenever you have boiling or condensation, this is related also to fluid motion, and this will lead to high convective coefficient. Example, when you have evaporation of water, if you observe the phenomena of evaporation and bubbles formation, you will see that you have the bubbling effect, and this will create a fluid motion within your system. So this is a very simple example of convection. You have a hot block and you are blowing air over it. You will have then heat transfer by convection. And as we discussed, the energy is first transferred to the air layer adjacent to the surface of the block by conduction, and then it is carried away from the surface by convection. So we can say that we have combined effect of conduction and convection in order to cool the surface. Here we summarize the formula used for the flux of convection, which is H delta T. And we can see here the velocity distribution. And as we discussed, we have formation of a boundary layer because of the resistance to velocity variation from 0 to u infinity. And this velocity distribution change is also if you want will be also with variation in temperature. So we also have formation of what we call the thermal boundary layer. هلا will not go a lot in details because you don't have the same thickness, of course, for the thermal boundary layer and the velocity boundary layer. You can see them in more details if you take the advanced heat transfer course that will discuss formation of boundary layers, velocity, and thermal boundary layer. It's also a very interesting course. But here we'll just go over the basics of heat transfer. That will be of help in our course material. So here we can see the difference between forced and free convection. Convection is called forced convection if the fluid is forced to flow in a tube or over a surface by external means such as a fan, a pump, a mixer, a wind. In contrast, convection is called free convection if the fluid motion is caused by buoyancy forces induced by density differences due to variation of temperature in the fluid. In addition, we also discussed that boiling and condensation involving phase change are also convective processes. Here we can see examples of natural versus forced convection. So if you just rely on density differences within your fluid, you have just convection current at relatively small velocity. While if you put a mixer, you can enhance the convective process and you will have larger convective coefficient. Now here, if we want, for example, to cool electric components, we have several options. We can blow air over them using a fan. So whenever you have a fan, a pump, any device that is producing power to blow your fluid, then it's forced convection. On the other hand, when you just rely on buoyancy driven flow, it's natural. You can tell me because mixed is much more effective forced convection, why we use natural convection, because it's free. Okay, we'll discuss also in energy efficient strategies, passive strategies. Whenever we want to reduce the energy consumption, we should try to go to passive strategies which do not rely on power consumption in order to produce any effect. So natural convection is true that it's less efficient than forced convection, but it has the advantage of being of needing no external intervention. So it's you can rely on free resources. And for example, we'll see that one of the important applications in buildings is trombe walls. In trombe walls, we rely a lot on natural ventilation. We can have some opening, let's say. Okay, for example, the idea is the following. Air is, let's say during winter, we want to heat the inner space. Okay, what we can do that during when we have sunny hours, okay, we have a glass material here that can trap energy from the sun. You have your circulate. You can open vents for your from your that separate your room from the trombe wall. Then this will allow circulation of fluid here in this zone, and because of the heating effect, this will create upward motion of air, and it will be supplied back to the space. So you can ensure circulation of air within your space, and air will be heated in this way. Okay, so we have a lot of applications that will rely on natural convection to produce free, if you want, or passive heating or cooling strategy. Okay. Now, the third mode of heat transfer is energy transfer by radiation. And also, you are familiar a lot with this type of heat transfer, and it's used also in a very wide range of applications, especially everything related to, let's say, PV cells, concentrators, rely a lot on radiation. So any matter that is at non-zero absolute temperature emits thermal radiation in the form of electromagnetic waves due to vibrational and rotational movements of the molecules. And then the radiation will depend on the level of temperature of the surface. And one of the most important examples of heat radiation is the sun, is the radiation from the sun. So the earth receives radiation from the sun by radiation effect. What is nice about radiation is it does not require any medium to be transferred. So even if you have vacuum, if you have two surfaces at different temperatures, and if you have vacuum between the two surfaces, you can have heat transfer between them, because in this mode of heat transfer, we have transfer of energy by electromagnetic waves. You don't need a medium between the two, not like convection and conduction. In conduction, you need contact. In convection, you need interaction between a moving fluid and a surface. While in radiation, you just need two separate surfaces at different temperatures, then you can have heat transfer between them. So, radiation can happen in solids, liquids, gases, and in vacuum, so it does not need a material medium, unlike conduction and convection. Now, a perfect radiator is a black body emitting the maximum of power at a specific temperature. So we'll see in this course that in general, the majority of surfaces that we have are not black bodies. They have a certain characteristic called the emissivity epsilon. And once we know epsilon, we can compare them to a black body. A black body is a perfect emitter and a perfect absorber. Okay, and in this case, it will emit the maximum possible power for a certain temperature, while a gray body will not be able to emit the maximum. It will emit a certain percentage of the maximum. This is why we'll see together that for a gray body, the emission is equal to the emission of a black body, which is the maximum possible emission, times what we call the emissivity factor, epsilon. So perfect radiator is a black body emitting at maximum power. When the energy density is integrated over all wavelengths, you know that we have a large spectrum of wavelengths. So to calculate the total radiation, we should consider the whole spectrum. The total energy emitted will be proportional to the absolute temperature to the force power. So from the analysis of radiation, if you integrate the flux over all wavelengths, you can come up with the total emitted flux. And you just have to know this. You should know that for a black body, when you do the integration over all wavelengths, you get the Boltzmann constant. And also, you don't have to memorize it. Okay, I will give it for you. The Boltzmann constant times the area times the temperature of the surface to the power 4. If we tell you that you have the surface act as a black body, you don't have to multiply by epsilon, because epsilon will be 1. While if it's a gray body, they will give you the emissivity. And they will tell you you have a surface characterized by an emissivity of 0.8, for example. Calculate the emitted power by radiation, for example. So all solids, liquids, and gases will emit, absorb, or transmit radiation at varying degrees. Radiation can be considered as a surface phenomena for solids that are opaque to thermal radiation, metals, wood, rocks, since the radiation emitted by the interior regions of such material can never reach the surface, and the radiation incident on such bodies is usually absorbed within a few microns from the surface. How we benefit from this information? As we were discussing in a while, if we have a surface and it's an opaque surface will not transmit radiation to the inner of the solid. It will keep it, if you want, it will absorb it within few microns of the surface. And then this absorbed energy can be transferred by conduction. Okay? While if we consider a surface that is not opaque, you can have what we call the transmitted energy. So in general, for the most general case, you have a surface, you have irradiation G that is hitting the surface. One part of this irradiation will be reflected. It's called rho G. And for example, whenever we do the design of buildings, we have some faces that are painted with high reflective properties because these surfaces can be exposed to the sun in summer. So depending on the orientation of the building, you have some facades that you don't want to have high absorption of irradiation from sun. That's why you can paint them with a paint with high reflective properties, because you will reduce a lot then the proportions that is absorbed and transmitted to your environment, to your indoor environment. So you have the reflected part, and rho, of course, will be depending on the material. You have an absorbed part that will remain within your material, alpha G, and you have a transmitted part that will be transmitted from your surface. It's tau times G. So we can say, if you want, that alpha, rho, and tau are percentages of distribution of the radiation. So we can write that rho plus alpha plus tau is equal to 1. And when I tell you we have an opaque surface will not transmit any part of the energy, so tau is 0. And then for an opaque surface, if you know rho, you can deduce alpha, because alpha is 1 minus rho. Okay, so now a gray body is defined such that the monochromatic emissivity epsilon of the body is independent of wavelengths and vary from 0 to 1, and it will be given for you. And how we define this emissivity, as I told you, it is the fraction of power emitted relative to another perfect radiator, which is the black body. So a gray body will emit a certain percentage of a black body, which is the emissivity epsilon. Now, all the solid opaque bodies around us are considered as gray bodies. This is why we will give you their corresponding emissivity. So the heat flux due to thermal radiation emitted from a surface of a black body can be expressed as EB equal to sigma times T surface to the power 4. And for a gray body, it's epsilon sigma times T surface to the power 4. So we take just a certain fraction of the maximum. Now, a problem that is widely encountered in case of radiation is when you have, for example, in a furnace, if you put a block and you want to heat this block by radiation, you have the walls of your surface furnace are at very high temperature. This is why they will emit radiation towards your block. Your block also will emit radiation out, but the net radiation will be in, because the flux that will enter is much larger than the ones that will exit. Why? Because we should consider the temperature. The temperature of the walls is much larger than the temperature of the box. This is why the absorbed energy will be larger than the emitted one. So the net radiation here will lead to heating of your box. And in such scenario, we'll see together that